Today we will learn about this module here, which is a module 12. Okay, in this module here, you will learn about interrupts. Okay, there are a few things that you need to know in the interrupt. The first one is the interrupts versus polling. Okay, what is interrupt and what is polling? Okay, what are the difference between the interrupt process and polling process? And then after that, you will learn about the interrupt units, which is a register that are required in order to do the interrupt programmings, and how to executing an interrupt, how to enable the interrupt, and how to disable the interrupts. And then there are a few interrupts here that you need to learn, okay, which is two interrupts. One is what we call here is external hardware interrupt, which is this external hardware interrupt will be triggered by your switches, okay. And the second one here, we have the timer interrupt. Okay, the timer interrupt will be triggered by the timer or delays. And then we're going to look at the interrupt priority. So what happens if more than two interrupt is triggered at the same time? Okay, which interrupt will execute, which interrupt will not be executed, and is it possible to do the interrupt inside interrupts? Okay, so without further ado, let's look at the uh, this slide. Okay, the introduction of the interrupts. So here, okay, a single microprocessor can serve several device tasks at the same time. Okay, there are two methods by which device receive a service from the microprocessor. Okay, means that a microprocessor can serve more than one task at one time. Okay, for example, if the microprocessor is currently do the program A, the task A, and suddenly the program B is request to execute, what happened here is, okay, the micro P, okay, will determine either this process B is an interrupt or a polling process. Okay, so let's look at what interrupts and what is the polling. Okay, we have a two process here, okay, which is satu ialah interrupt and the other one is polling. Okay, for the interrupt, okay, whenever any device need the microprocessor service, the device will notify by sending an interrupt signal. So an interrupt signal will be sending to the microprocessor in order to request an interrupt. Okay, sometimes we call it as a IRQ, which is interrupt request. Okay, so upon receiving an interrupt signal, okay, a request by the certain task, a certain process, so micro P will stop whatever it is doing and serve the device. Okay, and the program associated with the interrupt called the interrupt service routine or interrupt handler. This means that, okay, whenever the interrupt is occurs, okay, micro P will stop what it is currently do. Okay, they akan stop and it will execute the interrupt request, which is it will go to this interrupt service routine, do whatever in this interrupt service routine. Okay, after the interrupt service routine is finished, then after that, it will resume back to its main program or to the previous program it's currently stopped. Okay, so that is the definition of interrupts. Okay, then we have a polling process. Okay, so in the polling, the microprocessor continuously monitor. Okay, it means that it will continuously monitor the status of the given device. When the status is met, it perform the service. Okay, after that, it move on to monitor the next device until one is serviced. Okay, it means that this polling here, it will keep keep monitoring the status of a certain device. Either that device is requested to do the certain task. For example here, okay, I give you a very simple example to differentiate between interrupt and polling. Okay, let's you have a two, okay, process A and process B. Okay, let you have two process. Okay, process A is is your main process. Okay, which is a currently currently executed by your CPU. Process B is the interrupt request, and process C is a process which is for the polling method. Okay, let's look at the process A and process B dahulu. Okay, so currently, okay, your CPU is currently executing the process A. So in the middle of process A, okay, this is your process A. Okay, so in the middle of process A, okay, the process B request, okay, send a signal asking the CPU, okay, now I'm going to chip in. Okay, now I'm going to interrupt process A. So what happened here is what we call it, the CPU, okay, will stop this process A here. Okay, so the process A will be stopped and the CPU will go doing process B. Okay, so CPU will go here, do the process B until the process B is finished. Okay, and when this process B is finished, then what happens here is the CPU will go back, resume to this process A. Okay, resume the previous location that the process A is stopped. Okay, so this is for the interrupt. While for the polling, okay, so what happened here is you have the CPU currently doing a process A, and process B, process C is in the middle of process A. Process C is asking, okay, now I'm going to read to send this data, for example. But this is not interrupt. Okay, this is a polling. So what happened here is process A will continue do the process A even though the process B asking for to do some asking to execute the process C. What happened? The CPU will ignore until the process A is finished. Okay, when the process A is finished, then the CPU will go to this process C. So this is what happens when you do the polling method. Okay, so this is the difference between interrupt versus polling. Okay, for the interrupt, efficient use of the CPU, while not efficient use of the CPU. Why? Because when the interrupt happens, okay, the CPU will execute that interrupt, okay, without need to wait, okay, for the main program to finish. Okay, but for the polling, okay, the CPU need to wait a certain process is finished, then after that, the requested process will be executed. Okay, so then this one here, for the interrupt, can serve many devices, which each device get attention from the CPU based on the priority assigned to it. Okay, while polling cannot assign priority, so it checks all the device in round robin fashion. Okay, for example, this one here, interrupt. Okay, you have a process A, process B, or process 3, and these three processes have different priority. Process A is, for example, we have a highest priority, process B and C is lower priority. So when this process A and process B, process C is requesting, okay, to execute, give a signal to do the interrupt, the CPU will do the process A because process A has the highest priority. After the process A is finished, then after that, it will do the process B and process C according which one have a higher priorities. Okay, but this one here, okay, for the polling, it cannot assign a priority. Means that, okay, whatever proses that request dahulu dia akan executed regardless of its priority. Contoh, proses C request dulu, then followed by process A. Even though kita tahu process A has a higher priority compared to process C, but process C akan execute first. Then after that, the process A will be executed after the process C is finished. Okay. for the interrupt, the CPU can ignore or mask a device request for a service. Okay, if the CPU find that this request, the interrupt request is not that important, so it can mask that or it can ignore that request. But for the polling, every time the request is sent, the CPU cannot ignore. Okay, the CPU needs to do that process, even though the CPU know that okay, this process is not important, but the CPU needs to entertain that process. Okay, so that is the difference between interrupt and polling. And last but not least, avoid tying down the CPU. Thus, the waste time can be used to perform some useful tasks. Okay, and the polling wastes much CPU time by polling device that not need services. Okay, means that the CPU, while waiting for the interrupt signal, the CPU can do anything. Okay, it can do other tasks, other process while waiting for the interrupt to happen. But for the polling, it cannot do that. Okay, it needs to do all the process. Okay, and keep monitoring which process is requesting the CPU. Okay, either to send the data or to read the data. Okay, and then here, okay, tak nampak pula ni, so I just show this one here. Okay, so now we are going to look at the interrupt service routine. So for every interrupts, okay, so every interrupt, there must be a ISR, which is a interrupt service routine. Okay, since when an interrupt invoked or triggered, the micro P will run the interrupt service routine. So every time the interrupt request is being sent, and then CPU, okay, will execute the interrupt service routine. Okay, generally for every ISR, there is a fixed location in memory that pointed to the address of its ISR. Okay, so this group of memory locations set aside to hold the address of ISRs is called as interrupt vector table. So this is an interrupt vector table. Okay, if you can see here, there are a few interrupt inside of this interrupt vector table. Okay, started with a reset. So this reset here, the address is started at 0000 in your program memory. Then we have the external interrupt request. So this is a INT0, external interrupt request 1, INT1, INT2. Okay. So by looking at this here, okay, you can see the reset has a highest priority. Okay, so this is a priority. Okay, it has the highest priority, while bottom here have a lowest priority. Okay, so this so now, okay, what we're doing today, we're going to focus in on this. This is what we call it as an external hardware interrupt, which is INT0, INT1, and INT2. And then we have the timer interrupt. Okay, so this is the timer interrupt, which is timer 0 overflow, timer 0 compare mesh. Okay, timer 1 overflow and compare mesh, timer 0 overflow and compare mesh. So this is for the timer interrupt. Other than that, okay, we not covered in this process. Okay, now we're going to recap the flash memory. Okay, there are 32 kilobyte program in the memory for the flash memory in your Atmega 32. Okay, we see it divided into 3 parts. Okay, the first one here, this one here. Okay, this is for the reset and interrupt vector section, which is consists of a 84 byte. And then you have the application section. This is where you're going to put all your program inside in these sections here. And then the last but not least is a boot flash section. Okay, so the interrupt vector table, okay, will be located at this region. Okay, started from address 0000 until 002. it. Okay, here you see it. This is the addresses started from 000 sampailah 0028. All of this here will be stored inside this location kat sini. Okay, and this is how the step in executing an interrupt. So upon activation of an interrupt, okay, what happened here is the micro P goes through the following step. Mula-mula, okay, the first step here is it will finish the instruction it currently executing and save the address of the next instruction to the stack. Okay, so when the interrupt is triggered, what happened here is the CPU will take the address of the next instruction, which is from the program counter, put it dalam stack. Okay, then after that, it will jump to a fixed location in a memory called the interrupt vector table. Okay, the interrupt vector table will direct the micro P to the address of ISR. Okay, so what happened here is after put the addresses to the of the next instruction to the stack, the CPU will go to the interrupt vector table. Okay, and then it will take this, dia akan ambil, okay, the location of the interrupt being triggered. Contohlah, if you triggered the INT0, so the CPU will go to this address, okay, 002, and do the interrupt service routine. Okay, under this address, there will be one subroutine called the interrupt service routine. This is for the step number 2. Okay, step number 3, micro P will start execute the ISR until it reach the last instruction of the subroutine. Okay, this is for the assembly language lah. The last instruction for the sub ISR, we call it as a RETI, means that it's going to return from interrupt subroutine. But for the assembly language, for the C programming, okay, the last instruction for the ISR is followed by this close curly bracket. Okay, so upon executing this RETI ataupun this close curly bracket, micro P will return to the place where it was interrupt. Okay, it will go back to the place, okay, to the last instruction, okay, before it was interrupted, and then get the PC's address from the stack. So how the micro P know it needs to go back to this location? Okay, by take the addresses that already been saved on the stack previously, put it to the PC. So now the PC consists of this address, or the CPU tahu, okay, now we need to go back to this addresses. So it will go back to this place. Okay, so this is what happens every time you execute an interrupt. And this is the overview lah. Okay, so the overview here, I will show this slide here. Okay, so assume that this is the main program. This is the programs. Okay, this program here is written in assembly language. Of course, we are doing the interrupt programming by using the C programming, but the same process are similar lah for both assembly and C program. Okay, so here, if you can see on top of here, this is where your vector table, okay, you initialize the vector tables. You see .org0, so this is actually the location of the reset. Okay, looking back at the vector table, kalau kamu tengok balik, where is the vector table just now? Okay, reset is started at 000, and then is followed by 002 if you're going to use the interrupt request INT0 lah. If you're going to do INT1 next, what you need to do is you need to initialize your vector table at these addresses. Okay, since in this one here, okay, it's in this example, you're going to use the int0. So what happened here is, okay, you need to initialize lah this address 0802 to this subroutine EXO ISR. So this is the what we call here the interrupt service routine. Down here, this is the interrupt service routine for int0. Okay, you see here, currently the program counter is pointed to this address. Okay, means that the blue lines here is your program counter. Okay, and you see here, your stack pointer is not initialized to the lowest memory of your remnant. Sorry, to the highest memory of your remnant. Okay, it's somewhere around here. Okay, so what you need to do here is, okay, after you execute, okay, you see the program counter will keep increasing. Okay, so here what happened here is, so you initialize the stack pointer, all this thing here, and then initialize the input output dekat sini, enable the interrupt, okay, which is in this case here you're going to enable the int0. So this is the what we call here the coding to enable the int0, and this is to enable the interrupt globally. Okay, because before we use the interrupt, we need to enable all the interrupt that we're going to use, and this is the value that you're going to send out to R30 and R31. Okay, since int0 is an external hardware interrupt, for the external hardware interrupt, to trigger the interrupt, you need to put a switch here. Okay, you see here dekat PD2, there is another features for the PD2, which is for the other feature is for int0. Okay, which is at the port D pin number 2, you can trigger int0. And for if you connect your switch to PD3, okay, you can use that switch to trigger the int1, because in port D pin number 3, there is another features, okay, or function for the PD3. Instead of using it as an input or output port, it can use as a interrupt int1. Okay, so now int0 is being triggered. Okay, so it is active low. So what happened here? This value, okay, the next instruction here will be stored to the stack pointer, and now it will go to here. Okay, so what happened here is, once this one is triggered, okay, in this middle of the program here, you triggered the what we call int0. So what happened here? The next instruction, the address of the next instruction will be stored to your stack. Okay, you see here 000F, which is this address here disimpan dalam stack. And pada masa yang sama, program counter will go to address 002, which is go to here, and suddenly at this address it says that jump to this subroutine. So it will go to down here, okay, doing whatever under this subroutine. Okay, do all the instruction under this subroutine until, okay, it's going to execute the RETI. So what happens when it execute the RETI? These addresses here from the stack pointer will be, okay, load to your program counter. Okay, why? Because you're going to return back to this address dekat sini. Okay, so this is where we stop after the interrupt is triggered. So the CPU need to continue to this location. So what happened here? You see, okay, when the RETI is triggered, so the value from here will go here. Okay, so now the CPU know that, okay, now we're going to need to go to this address and return back to this location. So this is what happens every time you trigger the interrupts. Okay, any question up until here? Before we go more details on the interrupt programming. Okay, you need to know the what we call it, the overview of the interrupt, how the interrupt works. Ada soalan tak up until here? Okay, if no questions, okay, so next we go to this one, yeah. So let's look at the interrupt units in AVR. Okay, there are many sources of interrupt in the AVR. Okay, so at least 2 interrupt for the timers. Okay, which is for the timer, you can do either the overflow method or compare mesh method. And then there are 3 interrupt for the external hardware interrupt. Okay, so we have the INT0, INT1, and INT2. For INT0, okay, the location is at the PD2, port D pin number 2. So you need to put your switch to this pin here, okay, to trigger the INT0. For INT1, okay, it's located at port D pin number 3, and INT2 is at port B pin number 2. Okay, then we have another interrupt. We call it as a USART for the serial communication. And then SPI, okay, this is another interrupt, okay, to communicate between one IC integrated circuit with another integrated circuit, one IC to another IC. This is a protocol for the communication between one IC to another IC. We call it as a SPI. And then we have the ADC interrupt, okay, which is every time you do the analog to digital converter, you can do it by using the interrupt or by using a polling method. Okay, so now we're looking at this here. Okay, this is the port D. Okay, so this is the alternate function of port D. Okay, instead of using the port D as an input and output port, you can use this port D here with this alternate function. Okay, now we are going to focus on this alternate function, which is the INT1, external interrupt 1, and INT0, which is external interrupt 0. Okay, so this is the location dekat PD3 and PD2. Okay, another alternate function is if you're going to use to transmit or to use a USART, okay, you can put it to the PD1 and PD0, and this is for the timer. Okay, for the counter you can put this location, this port here. Right, and this is the recap for the ATmega 32 pin out. Okay, for the INT0 and INT1, okay, we need to put it here. Okay, the switches must be put at this location, pin 16 dengan pin 17. While if you're going to use the INT2, okay, you need to put here at a PB2. Okay, and these are some others alternate function lah. For example, for the port A, okay, we can use this port A here as an analog to digital converter. And if you're going to use what we call here to transfer data, okay, as a transmission, okay, you can use this tempat here. Okay, MOSI and MISO, this is for the SPI and etc. Okay. So now you're going to look at the interrupt programming in C. Okay, so in C language, okay, there is no instruction to manage the interrupt. Just need to add the following in your program in order to manage the interrupt. Okay, first, what you need to do is you need to include this header file here. Okay, so this is the first step. Okay, include avr/interrupt.h. Okay, so this is the first step. Okay, every time you're going to every time you're going to do the interrupt programming. Okay, and then the second step here, okay, after you include this header file, okay, under the main program, okay, you can start with the GPIO setting, okay, which is initialize your GPIO, initialize your input output. Okay, if you're going to use what we call here external hardware interrupt, which is INT0, INT1, and INT2, make sure that you initialize your INT1, INT0, and INT2 as a input port, because there is where you put your switches to trigger the interrupt. Okay, and then step number 3, okay, you need to enable the interrupt. Okay, there are 2 locations to enable the interrupt. Okay, satu, if you using the hardware or INT, okay, you need to enable the type GICR. Okay, so if this is the first lah, this is where you're going to enable the interrupt. Or if you're going to use a timer interrupt, okay, you need to enable it the type TIMSK register. Okay, so this is the first thing. Okay, enable the interrupt. Then after you enable the interrupt that you're going to use either at the GICR or TIMSK, then the second one here, you need to enable the interrupt globally. Okay, how to enable the interrupt globally? By putting the SEI. Okay, means that use the SEI to enable, okay, which is we're going to set I bit in status register. Okay, inside of status register, your SREG, there is a I bit here somewhere around here. Okay, so you need to put 1 to this I bit to enable the interrupt globally. Okay, so means that you need to enable at 2 location lah. First, dekat the register interrupt either it on the GICR or TIMSK, and then satu lagi dekat status register. Okay, and step number 4, then after that, okay, write down your ISR, your interrupt service routine. Okay, which is you need to define your ISR. Okay, to write an ISR, should write in the following structure. So ISR and followed by the interrupt vector name. Okay, make sure that the name is correct. Okay, make sure that you need to follow the standardized name lah. Jangan pakai nama. Jangan pakai the ISR name suka-suka je. Okay, which is you create it by your own. If you create the ISR name by your own, then the interrupt will never happen. Okay, so for the interrupt vector name, must use the ISR name in this table here. Okay, so this is the table that you need to use. Okay, this is the vector table name. Okay, for example, if we're going to use the external interrupt request 0, make sure that the name is follow this name standard, which is INT0. Okay, so this is an uppercase or lowercase punya ni sensitive. Okay, make sure that if you use the uppercase, then you use the huruf besar, and if it's have a lowercase, then you need to use the huruf kecil. So contohnya INT0 underscore vet, this for the INT0, and for the INT1, which is the ISR name is INT1 underscore vet, and INT2 is INT2 underscore vet. Okay, if you're going to use for the timer, this is the name for the timer interrupt. Okay, make sure that you refer to this tables here for the ISR vector name. Okay, up until here. Any question up until here? Okay, if no question, next, okay, we are going to look at how to enable and disable interrupt. Okay, as I mentioned earlier, there are 2 locations to enable the interrupt. First, inside the status register, and the second one in the interrupt register, either GICR or TIMSK. Okay, so upon reset, all interrupt are disabled, or sometimes we call it as a mask. Mask means that will disable. Okay, kenapa? Upon reset, all interrupt are disabled because all the registers inside of your IO register is reset, which is the value inside of your IO register are zeros. Semua sekali zeros. Every time you turn on your microprocessor, every time you reset your microprocessor, all the register value inside of your IO register, your GPRs, okay, your RAM will be 0. Why? Because they are volatile memory. Okay, ingat lagi tak volatile memory? Volatile memory means that every time you turn on your processor, all the memories will be erased. Okay, so none will be responded to by microP if they are activated. Why? Because your interrupt been disabled. Even though you press your INT0, INT1, INT2 switches, it will not trigger. Okay, so the interrupt must be enabled, or sometimes we call it as an unmask, for microP to respond to them. So how to enable the interrupt? Okay, first let's look at the status register. Okay, so this status register responsible to enable and disable the interrupt globally. Okay, as I mentioned here, okay, there are two locations to enable the interrupt. Okay, satu inside of your status register, and the second one here is inside of your interrupt register. Okay, for the interrupt register, you have two interrupt register here, either GICR ataupun TIMSK. GICR if you use the hardware interrupt, which is INT0, INT1, INT2. For TIMSK, this is for the timer interrupt. So now we're going to look at this status register dahulu. After that, we're looking at the GICR and TIMSK. Okay, for the GICR, you need to enable this bit here, bit I. Okay, which is bit I is a global interrupt enable. Means that inside of this status register here, you need to put one, okay, to this I. Okay, you need to set this I here sama dengan 1 to enable the interrupt globally. Okay, so the bit 7 in status register must be set high. Okay, put 1 to allow interrupt to happen. Okay, how to do that? Okay, by using the instruction which is SEI. Okay, every time you use the SEI means that you're going to set I bit sama dengan 1. Okay, to disable, how to disable? Okay, put 0 lah by using the CLI to your bit 7. Okay, automatically all interrupt are disabled. Okay, and there are some more IO register holding the interrupt enable bit even though I sama dengan 1. Okay, even though you put the I, okay, even though you enable the interrupt inside of your status register globally at this here, okay, by putting I sama dengan 1, and this one here you not enable, what happen is the interrupt will never occurs. Kenapa? Sebab dia punya condition is need to enable both location. First, dekat interrupt register, and the second one inside of the status register. Okay, so now you need to enable to this location lah, GICR and TIMSK register. Okay, so let's look at this. Okay, so this is the TIMSK register. Okay, which is a timer interrupt mask register. Okay, so this is the location lah. Okay, if you're going to use the timer 0 overflow, okay, you need to enable at this bit here. Timer 0 compare mesh. Okay, you need to enable at this bit here. Okay, and then if you're going to use a timer 0, okay, sorry, timer 1, okay, overflow, okay, so you need to do it around here. And if you're going to use the timer 2, okay, you need to enable at this location, either overflow method or compare mesh. Okay, so this is the location lah. No need to remember this this register, because this register will be given in the appendix every time you every time in the final exam on or in the what we call it in the test. Okay, no need to remember the these registers here. Okay, no, just need to know where to enable the location for the certain interrupts that you're going to use. Okay, and then the second one is, okay, if you're going to use the external hardware interrupt, so this is the location that you need to look at. Okay, so first we have the INT1. Okay, bit 7 is INT1. So this is for the external interrupt request one. Okay, to enable, macam mana nak enable? Okay, you need to put one lah dekat sini. Okay, so this is INT0 and this is for INT2. Only 3 bits saja kat GICR that you need to look at. Okay, while the remaining of these bits here, okay, just simply put 0. No problem. Only this bit that you need to enable according to the what we call here, the interrupt that you're going to use. Okay, so that is how regarding the interrupt register. Any question up until here before we go to the external interrupt programming? Ada soalan tak? Okay, if no question, okay, then we go to this external interrupt programming. So this is how to do the interrupt programming. Okay, there are 3 external hardware interrupt. Okay, so this is just for the recap lah. Okay, which is we have the INT0. Okay, where is to put the switches for INT0 dekat mana? Pin PD2. Okay, so this is where you need to put your INT0 punya pin, your switches, and the vector table is a location at this addresses 0x02. Okay, then we have a INT1. Okay, which is located at a PD3, and this is the vector table location at this address 04. And INT2, please make this correction here. This is a INT2. Okay, which is located at port B2, and the vector table location is 6. Okay, so this is where you need to initialize your GPIO every time you use your interrupts. Okay, so the hardware interrupt must be enabled before they can take effect. Okay, so the third step here, okay, as we can see here, the third step is enable the interrupt registers. Okay, so to enable interrupt register, you need to enable dekat mana? GICR. Okay, so this is the bits lah that you need to enable. INT1, INT0, INT2, which is dekat bit 7, 6, and 5. How to enable? Put 1 to this bit, and then you already enable the what we call here, the interrupt. Okay, let's look at this what we call examples. Okay, assume that, okay, now you're going to enable the, you are going to use the INT0. Okay, macam mana nak enable INT0? Okay, first, okay, we need to figure out lah dekat mana INT0. Okay, so this is your GICR. Okay, we know that this is a INT1, this is INT0, and this is INT2. Okay, so this is the location of INT0. So what number that you need to put here? Okay, to enable, you need to put 1 because you're going to enable the INT0. What about the others interrupt? Okay, other interrupt, you just put it with 0, and the remaining of this bit here you put 0. So how to write down the program, the coding? By using a C programming, you can simply write GICR equal to 0B for the binary number. Okay, so easy for us, better to use a binary number lah compared to hexadecimal number. Kenapa? Senang kita nak refer back either betul tak INT0 is been enabled. Okay, so the value is 0, 1. Okay, so this is where the INT0 punya location. 0, 0, 0, 0, 0, 0. So this is the value to enable INT 0. Or sometimes, if you don't want to use the, what we call here, this binary representation, okay, you can use the hexadecimal, which is kena tukar dulu lah. Okay, convert this value here to what we call to hexa representation, which is by using the add 4 to 1 method, add 4 to 1 method, so you will get 0, 8, 0x 4, 0. Okay, so this is same lah. Okay, this is by using the binary, and this is by using the hexadecimal. So the INT0 is a low level trigger. Okay, every time you use the hardware external interrupt, make sure that it is you need to use the active low switches. Okay, make sure you use the active low switches. Kenapa? Sebab this interrupt here is a low level trigger. Okay, whenever a low signal is applied to PD2, okay, the controller will be interrupted and jump to INT2 vector. Okay, in the to service the ISR. Okay, for example, okay, if you're going to use the INT1 and INT2, how to do that? How to, what we call here? How to enable INT1 and INT2? Okay, to enable INT1 and INT2, was simply like 0B1, this is for INT1. Okay, INT0 disabled, INT2 you enable, the rest you put 0. Okay, which is sama dengan GICR 0x 8 tambah 2 is 10, which is A 0. Okay, so this is to enable INT1 and INT2. Okay, if you're going to enable all the interrupt, okay, you're going to use for all the interrupt, INT1, INT0, INT2. So what you're going to do? Okay, just simply write GICR sama dengan 0B11100000. Okay, so all the interrupt you enable, ataupun GICR sama dengan, so this is OX E 0. Okay, so this is how you're going to do a programming, okay, in order to enable the external hardware interrupt inside the GICR registers. Okay, so I think we stop here. Okay, next class we will continue with this what we call it, these examples. Any question up until here from you? Ada soalan tak?